to start, let us look at the structure of a D flip-flop. So here we have a simple D flip-flop composed of two latches in a master-slave configuration. We have added wiring here and here to implement the set reset functionality. This wiring ensures that we can set the flip-flop to 1 or clear it to 0 regardless of the D input and sometimes regardless of clock signal. We could build this structure really and using hierarchical design, but today we will focus on describing this behaviorally, which is more commonly used. So let us start by implementing our design. So here we have defined our module, dff underscore reset, and we have given our inputs, that is the clock, t, and we have given a reset underscore n, which we will be using for asynchronous. So it worked as an active low signal. So let us see how it will work. So at the negative edge of the clock, we want the Q equal to D. So we are implementing this flip-flop with this functionality. We want that when there's negative edge of clock at Q, we get the value of D. So now we have defined the Q reg, which is the current value, and Q next is the next value. And now when the reset will be low, the Q reg will be 0, and otherwise it will be configured with the next value. So how we will get the next Q next, let us see. So now how we will update the next logic. So whenever there will be a change in D, the Q next, the next logic will be updated, and the Q reg will be updated only at the negative edge of clock. So let us now apply the asynchronous reset on this. So now how will this asynchronous reset work? So we have defined input reset here. So whenever there's a so how will this asynchronous reset work? So, asynchronous means regardless of clock. So, whenever there is a clock, so it do not care what the clock value is. The moment we assert the reset, it get resetted. That means the flip-flop becomes 0. So now, as we have introduced a new reset uh, input here, we have also updated the sensitivity list here. So whenever there is the reset is low, the Q reg will be updated with 0. So now how can we add a synchronous functionality to this D flip-flop? Let us see. So synchronous means that the circuit that this will be dependent on the clock. So whenever the whenever this reset is asserted, regardless of this negative edge of clock, the the flip-flop will be reset. So as the synchronous means it is dependent on clock. So here in as you can see in the connectivity in the sensitivity list, whenever there will be a change in D, this value will be updated. And whenever there's a we assert the clear button, this will whenever clear is low, then Q next will be updated with 0. So now let us implement this design on Yosys and see the synthesis process.
So now we will run our design with GTK wave. So let us see. So this is our test bench. So in this we first instantiated our unit under test. We generated the clock and then we generated different D value at different times as you can see here. Then we implemented the asynchronous reset functionality. Then here we implemented the asynchronous we implemented next logic with the synchronous set, and this is the output logic. And we used the Verilog command to compile our designs, and we got an output in DFFOP file, which is here. As you can see, it is we got it. So after that, we used the GTK wave command which gave us output like this. So here, uh, whenever the reset is 0, we get our Q0 as shown here. And whenever the set is 1, our Q is 1. So, so after that, we invoke the Yosys tool as shown here, and then we run the read liberty command. So why did we run this command? So this loads the technology library file which contains the standard cell definitions and timing information for the specific process technology. So in this case, we are using Sky Water 130 nanometer process, and the lib flag specifies that the file being read is a Liberty format library. And the purpose of this is to provide Yosys with the information needed to map the synthesis design to the actual hardware components available in the specified technology library. So next, we read our file. So this command reads the file containing the design description of the D flip-flop with a asynchronous reset. And the purpose of this is to load the Verilog design into Yosys for processing and synthesis. Next, so I run the synthesis command here as you can see. So this command initiates the synthesis process. So Yosys will synthesize the entire design starting from the this top level module. So to convert the high level description into netlist of logic gate that implements the same functionality, and then we use what the command. So these are our statistics of our design. So after running the synthesis, we run this dff libmap command. So this command maps the D flip-flops used in the synthesized netlist to the actual flip-flop cells available in the technology library specified. So the Liberty flag points to the same Liberty file used earlier. So the purpose of this is that the synthesized flip-flops correspond to real physical flip-flops in the target technology. So After that, we run the abc command. So here is our abc liberty command. So this command runs the ABC tool, which is a logic synthesis and optimization tool integrated into Yosys. So the Liberty flag again points to the Liberty file here. And the purpose of this is to perform additional logic optimization and technology mapping to further refine the synthesized netlist. And then to see our graph with representation of our design, we run show. So after that we get this output.